Okay, so we have, just like the question at the end of class yesterday, we have a sled, okay, that at the top of a hill is at rest. And this hill is 40 meters tall, right? We are being asked to calculate how far above the bottom of the hill is this sled, okay, when it is moving at 16 meters per second a little bit later. All right, everybody with me there? We'll call that givens. If they wrote down other givens, that's fine, but as long as they have some givens written down, when I do conservation of energy, I draw pictures. I don't draw pictures very often for obvious reasons. Okay. The energy at the top and the energy at the bottom, mechanical energy at the top and bottom, are equal. Okay. At the top, okay, we have EK initial plus EP initial. At the bottom, we have EK final plus EP final. Are any of these zero? Which one? EK initial is 0 because it was at rest. All right, so that makes our life a little bit easier. There's one less thing to be moving around. I'm trying to solve for the final height, which is part of EPF. So what should I do with EKF? I should move it to the other side. So I'm going to have the initial potential minus the final kinetic equaling the final potential energy. Okay, now I'm going to plug in my formulas. So m times g times hi minus 1/2 mvf squared equals mghf. What do I not need? M, which is good because I didn't even give it to you. Okay, so we'll cross it off. Okay, and I'm looking for hf. What do I have to do with g? Okay, divide over. Oh, sorry, I've been not telling you where the marks go. 1 mark there for identifying it as a law of conservation of energy question. Okay, a mark here for showing that they had to move one of the energies over. Okay, let's go with a mark here for putting in the formulas. Or sorry, for the manipulation. Sorry, for the manipulation. Okay, so we've got the manipulation here. Okay, then we got to plug in the numbers, or up to 4 marks. Okay, so 9.81 times 40 minus, not plus, minus 1/2 times 16 squared, okay, divided by 9.81. Give them a mark for putting the numbers in correctly. Okay, that equals HF. Okay, so we have 9.81 times 40, okay, minus 0.5 times 16 squared, divided by 9.81. All right, so this thing is going to be 26 point, well, let's say 27.0. It's going to round up 27.0 meters above the ground. That's their 6th and final mark. Yeah, if they left it as 26.95, I didn't specify the decimals I wanted. Okay, so mark out as 6, let him see it, and then I want it on the desk in front of Sean, please.
I'm not sure how to mark this.
Okay, so the problem that we're investigating here today, for some reason I don't have it on there, okay, but the problem we're investigating is how much potential energy is converted to kinetic energy in a mechanical energy conversion. Okay, we're going to be converting one form of mechanical energy into another, that is potential into kinetic. Okay, we want to find out just how effective that conversion is going to be. Right, so that's the problem we're investigating. Now, for this experiment, okay, we are going to essentially we're going to put this cart at the top of this ramp. We're going to build this ramp, and then we're going to put it at the top of the ramp. As a result of doing that, what have we now put into this system? We have put potential energy into this system. Does everything else in this lab depend on how much potential energy I put into this system? Okay, so in other words, I've done something very important experiment-wise regarding the potential energy of the system. Okay, because nothing else will happen if I don't do this as the experimenter. Okay, I see a few people nodding now, so they're starting to get it. Okay, What we're watching for, okay, we're watching for a couple of things. We're measuring several different things. So there are going to be several responding variables, one of which is the most important. But in order to calculate it, okay, we have to measure a whole bunch of other things. Okay, some of the things that we're going to measure are going to be the distance the cart travels, how long it takes it to come to a stop, okay? As a result of those two variables that we can actually measure, we'll be able to calculate how much kinetic energy the cart has at the bottom of the ramp. Okay? So which one of those variables is the most important of the responding variables? No, I'm using distance and time to calculate kinetic energy. Kinetic energy, I mean, these are the two things we're comparing, right? We're comparing potential energy and kinetic energy. That makes them the most important variables, okay? One of them is responding and one of them isn't, okay? Now, looking at this setup, what are some things that I don't want to have change while the cart is going down the ramp? Yeah, I don't want to change the height or angle of the ramp at any point. Okay, that ramp needs to stay the way it is. If I pick up the end of the ramp while the cart is rolling down, I'm going to change the amount of potential energy that's in there, and I don't want that. Okay, so I've got to make sure that the ramp stays the same. Okay, you think of a few other things that might affect, okay, the kinetic energy of the cart or the potential energy of the cart if they're not controlled. Okay, explain, remember, how we're controlling them, what their effect would be. Now for the hypothesis, okay, if and then statement. The whole premise here, the whole idea that we've been working on the last couple of days is that mechanical energy is conserved in all energy conversions. Agreed? But what world are we living in when we say that? We're living in the perfect physical world. We know that in the real world, it's not all the potential we start with is not gonna end up as kinetic at the end, okay? But we have to at least go with that idea as being the fundamental idea we're working on. So the if part should probably talk about the law of conservation of energy, okay? And what it says about what's gonna happen here. Okay, the and part, as always, describes the experiment. Okay, the then part should tell me if the law of conservation of energy says that this is going on and this is done, then what's going to be the relationship between EP and EK? Okay. So if we're talking about this in terms of the perfect physical world, is our hypothesis going to be right? Okay, and that's all right. Okay? It is okay for a hypothesis to be found to be incorrect. It just means that we have to think a little more in our conclusion about why it isn't. Okay? All right, the materials you're going to be working with, okay? First off, you're going to have a dynamics cart. There's two different kinds of dynamics carts in the box over there. You want the ones that look like this black one, okay? They're long and black, not the short silver ones, okay? So you're going to grab one of those. They all have a mass of 0.470 kilograms, just to save us bringing out the triple beam balances and actually taking all of their masses, okay? They're all exactly the same, okay? They're all 0.470 kilograms. Okay. We're going to have these beautifully constructed ramps. I say that because Mr. Dickey and I built them. Okay, they're awesome, and they're way cheaper than buying them from the scientific company that gave us the crappy spring scales. Okay, they want $250 for their ramp. We built all of those for $50. Again, that's what happens when you cut money from education. Teachers have to get creative and learn how to use a router. Yeah. Okay. Anyway, they're nice and straight. Mr. Kruger helped us. Okay. We took shop for a couple of days. Then you'll also have a meter stick. Okay, because we're going to have to measure the initial height of our ramp. Okay, so we need a meter stick for that, and we're also going to have to measure how far the cart travels. Okay, at the end of the ramp. So we need quite a bit of measuring to do there. Okay, obviously you have to have your calculator, and you need to use the stopwatch on your phone to time how long the cart is going to travel for. Okay, now when do you need to start the stopwatch? Actually, when the cart gets off the ramp, that's when you have to start it. We're only concerned with the part of this experiment where the cart is slowing down. Okay, the energy conversion happens from the top of the ramp to the bottom of the ramp, but what we can't actually measure or calculate how fast the cart was going at the bottom of the ramp. We don't have any tools for that. Okay, so what we're going to do instead is figure out how far it takes and how long it takes for the cart to stop, and then we're going to use the work done in stopping the cart to figure out how much energy it had when it was at the bottom of the ramp. Okay, what's stopping the cart, by the way? Friction. Friction's the only force that's important that's acting on the cart once it gets to the bottom of the ramp. Friction will take away all of the cart's energy. So if we can figure out how much work was done against friction, which we can, okay, we'll know how much kinetic energy it had at the bottom of the ramp. Everybody follow? Okay, so that's what we're doing to figure that part out. Okay, to figure out the potential energy, what are we going to do? MGH, yeah, it's going to be really easy. Okay, we're going to measure the height of the ramp, take the mass of the cart, multiply by 9.81 times the height of the ramp, and we've got the initial potential energy of the ramp. Okay, or of the cart, sorry. Good. As long as you time it consistently, I would say yes, the front, probably the front of the cart. Your reaction time is going to make it so that it's kind of the center of the cart anyway. But yeah, I get what you're coming from. Try and be as consistent as possible. Okay, that might possibly be a source of error. Right? Okay, so potential energy. Okay, so keeping in mind that there are several variables you'll need to record in order to calculate energy. So to calculate the potential energy, we need the mass of the cart and the initial height of the ramp, and obviously acceleration due to gravity. Okay, to calculate the kinetic energy, we need the mass of the cart. Okay, we need the distance traveled by the cart after it leaves the ramp. Okay, and the final velocity of the cart, which is 0. Okay. And also we need the time of travel. Okay, things that you're going to need to calculate and how you're going to calculate them. You're going to need to calculate the acceleration of the cart. To do that, you're going to use a formula we haven't used in Science 10. It's a Physics 20 formula, but you just have to plug numbers into it. You don't have to do anything else with it. Okay, that formula is going to be that A equals 2 times the distance over t squared. Okay, it's on your lab sheet there. All you have to do is take the distances you measure, the times you measure, okay, and plug them into that formula to calculate the acceleration of the cart. Everyone okay with that? Okay. Then we're going to calculate the kinetic energy using the acceleration of the cart. And here's how we're going to do that. Work equals force times distance. Okay, we've been using that formula a whole bunch. And we just said we're going to use the work done by friction in stopping the cart to calculate how much energy it had. Okay, well, to calculate force, formula we haven't used, this is the only time. It's on your formula sheet. I said we're only going to use this formula one time in this whole unit. Today's the day. Okay, mass times acceleration calculates force. Mass times acceleration times distance calculates the work done against the force of friction. Okay, and that will also calculate then our kinetic energy. All right, everybody follow there. So those are the calculations that you will have to do. Okay, they're all written up there. They're easy to do. You don't have to manipulate or think. You just have to plug numbers in. Okay, simple calculations on those. Okay. So the procedure is set up the ramp apparatus as shown at right. The height should be around 15 centimeters. Please make sure it isn't higher than that. Higher than that, and there isn't enough room in here for the cart to stop, and it hits the wall, and that doesn't count, okay? Because then the wall did the work, not friction. Okay, so we have to make sure that our ramps are really no more than 15 centimeters high. Okay, put the dynamics cart, not in the rubber band. Whoops, that's from the old version of this. On the top of the ramp, not in the rubber band. Okay, and then have the timer cue the person holding the cart to release it. Okay, let it roll down the ramp. Start timing when the cart leaves the ramp. Really important that that is when we start timing, not while it's going down the ramp. We don't want that part, just when it leaves the ramp. Again, as a matter of reaction time, I would just, as soon as you see at least part of the cart leaving the ramp, start the timer. Okay, because it's going to be moving fairly quickly. Okay, and as long as you're kind of center of the cart, when the cart stops, stop it. That'll be good enough for our purposes. Okay. All right. So then measure and record how far the cart traveled from the end of the ramp. My suggestion would be don't measure each trial one at a time. I would run that cart down the ramp and put a mark on the floor. Okay. So just take a board marker. Okay, and just mark on the floor where the cart stopped. Doesn't matter whether you measure the front of the cart or the back of the cart, as long as you measure it the same way every time. Okay, everybody follow me on that. Okay, so just put a mark on the floor, like a little line, and then trial 1. Okay, mark trial 2, mark trial 3, because I think it says in here we're going to do 4 trials, right? Yeah. Okay, so we're going to do 4 trials of that. Once you've got all the marks, then you can start measuring with the meter sticks. Okay. All right, then you'll have a chart, okay, that looks like the one in your lab. I'm just going to go to this one because it looks. Is it that one? It looks like that? Yeah. Okay. So distance traveled, okay, the amount of time that took, okay, and then we use that to calculate the acceleration using this formula here. So we go 2 times the distance, okay, divide that by t squared. That'll give us our acceleration. Okay, so we fill that into this column here, okay, and then we average it. Okay, so calculate the acceleration, right, for every cart, and then average the accelerations. Everybody with me there? Awesome. Because it's the same every single time, right? You're putting the cart on top of the same ramp every trial, so we only need to do that one once. Yeah? Okay, and then for EK, right, you're going to take mass times acceleration times distance. So use your average, okay? Use your average acceleration that you calculated here, your mass, and average distance. Okay, everybody follow me on that one? You know what? No. No. Sorry, I said that backwards. Calculate the acceleration for every cart. Calculate the kinetic energy for every trial, then average the energies at the end. Sorry, I said that backwards. Okay, so calculate the acceleration. Okay, don't bother doing an average acceleration. Okay, calculate the kinetic energy for every trial, and then average them down here at the end. Okay. Well, you'll need the no, you won't. Right, you won't need to do these averages here. So these will stay blank. Okay, these ones won't be averaged. You're going to average your kinetic energy and compare it to your average potential energy, which is the same every single time. Okay, those are the 2 numbers in the end that are important. Okay, it's calculating those. Okay, so your analysis here. Okay, calculate the work done in putting the cart at the top of the ramp. Show your work. This will be your potential energy. That's not a hard calculation, and you had to do it in the chart anyway. Okay, so you're basically filling in the chart for question number 1. Okay, calculate the acceleration of the cart. So basically, again, filling in the chart. So a lot of these analysis questions are basically just filling in the chart. Just show me your work, okay, for at least one calculation, just so I know that you're doing it right. Okay. For number 3, calculate the kinetic energy. Again, show your work, put it in the chart. Okay. Outline how you determined the potential and kinetic energies of the system. Be detailed. I've already gone over that. Okay. I said that we were calculating the kinetic energy. Okay, by looking at what happened with friction, okay, and obviously putting something at the top of a ramp gives it potential energy. Just talk about that, explain, changes in energy and work. Work energy theorem is basically what they're asking to explain there. Okay, did the potential energy of the system equal the system's kinetic energy? Why or why not? Okay, suggest reasons for your results. Okay, so in that question, that's the question that's saying, where did the energy go? Okay, so while you're doing this, watch it carefully. Maybe take a video of it. Okay, and then later on when you're working on this question, you can look at it, listen to it, and go, okay, maybe it lost some energy there. What happened with the card? It was doing something funny here. Would it have lost energy when it did that? Okay, all of that kind of stuff. Take it, if you've got like a newer phone and you can take it at 60 frames per second. Okay, you can set that up on the iPhone. Okay, take it. You can slow it down. Do it in slow-mo. Watch it really slowly later. Okay, and have a good look at it and see if there's places you can identify where energy might have been lost. Okay, questions on what we're doing there? Okay. All the equipment you need is over there. Okay, get it set up. I would say our best bet here to make the best use of space would be to go down the aisles, okay, like this. The carts go reasonably straight, okay, but if we find they're starting to go crooked or something like that, we might be able to go across to the chem lab. But let's set it up down the aisles first, okay, and see how that goes. 4, 5, yeah. I've got eight ramps there. So.